just something. But it turns out those are all awesome. Like anytime I don't get the machine parsable output means that the debugger's gone wrong, and that means that it couldn't disassemble, which is automatically, effectively means it's running junk. So almost all of those are worth looking at. And yeah, the ka-ching. Like this is where it should say like above exploitable. Like 0101, that's like straight out of my fuzzer. It's one of my binary corner cases. So basically I've found a please set EIP to this value structure. And that's nice. Like if you're going to start exploiting word bugs, then this would be like your Tinker Toys. But you know, crashes that cool must be pretty rare, right? You know, how often would you really get like full control of EIP? And you know, not that often, just like 700 or 800. That's the ones in red, where it looks pretty much like it's taken corner cases straight from my fuzzer. The ones in purple look like pretty much Unicode text. The ones in green look like ASCII text. And the rest are probably bad as well, but they're all funny. Okay, that's my 30-minute warning. So yeah, there's some bugs. Unfortunately, the only way you can now collate these is by going back through stack trace, because it's no good looking at the EIP anymore to collect them into issues. So you've got to go back and look as much as you can at where the bug came from. So you might find that like 30 of these came from one issue, which you can like kind of isolate by stack. But in a lot of these cases as well, the stack is blown. So you've got a problem where you can't even work out where it came from until you actually open it in a debugger. Then you can go to where the stack should be and try and like stick it back together with sticky tape. So yeah. Now all of those offsets, unfortunately, because like, well, I wouldn't say I'm a nice guy, but like I'm not a complete evil bastard. All of those offsets are now sort of dead-ish, so they're on death row, so I wouldn't bother trying to like go and exploit them. In the spirit of coordinated disclosure, they don't call it responsible anymore. Tom? We have now responsibly disclosed the bugs to Microsoft. And next we're going to talk about like my crazy research, which may or may not be useful. But are there any questions on just the bugs? Yo.
Do you often find it useful to tell Microsoft about something just so it stops getting in the fuzzer's way?
That is an awesome question. It's like, do you like to like disclose bugs to get rid of bugs that you see all the time? We already have, and they don't fix them because they're chaff and they make life harder. There are at least 3 crashes that I see all the time. Between those 3, I've probably got 40,000 of the 60,000 you saw. And I just like bin them because I know them. In other cases, I think that they deliberately make it fault. Like it's like, whoa, something wacky is going on, like read null, read null. Again, to make it harder for attackers to get to the real bug, which is an entirely valid strategy in my opinion. So yeah, but it's a very good question. Cool. Okay, crazy research time. This is all his fault. Dave, Justine's husband. So we're talking in the back row in Taiwan. And he's like, oh, I got one of my Dave ideas that I'll tell you, and like, then you can go away for a year and see if it works. So the idea is you take each basic block and number it. You get a run trace basically. So you run the program once with the file and once with the template. So that gives you 2 signals, right? NSA guys are like wacky about signals. And so once you've got those 2 signals, one of the clean file and one of the crashing file, you can look at them and do interesting things. And he's not really sure what they are, but you know, maybe like subtractive frequencies or maybe like a hidden Markov model or a neural network. Okay. And like make it tell you something. So exactly. So the first thing you got to do, I guess, is to like get your run trace. We initially used Dynamo Rio, which is super fast and has like a nice clean API. It's horrible to work with on Windows. Like, it needs CMake and MSys and all kinds of stuff you really don't want to be messing with. And then it like just stopped working for no apparent reason. So we gave Dynamo Rio the finger, and we're now using Pin. Pin is a weird looking API, and it's a little slower, but just because of the difference in the way it works, which is much more complicated than I'm going to explain here. But it's more reliable, it's easy to build tools, and it's cross-platform. It also is apparently what all the cool kids are using. Like, I know Immunity are using Pin. Pin? You using Pin? No? Okay, at least, well, half the cool kids. So I would recommend, if you're going to get into it, then Pin is probably a better bet, in my opinion. The runtrace side was actually written by the Grug, who's like in another room right now talking about GSM. So he's like my go-to write this C code for me guy. So once you get the runtrace, you run into some problems. So the streams of numbers are really, really long. We're talking like gigabytes of dump. Fast Fourier transform and hidden Markov model were red herrings. Neural network was just like a dumb idea. The hidden Markov model, right, like we can directly observe the state. So trying to guess it from a hidden Markov model turned out to like not really be a good idea. And you'd be surprised, well, you probably wouldn't. Visualization, which normally saves the world, is very unuseful. Like, here we go. Like I scanned this with a barcode reader and looked to see if the bug came out, but it didn't. And here we go. Like, you know, imagine that one of these edges is red. That'll like tell you stuff, right? So yeah, visualization, not so good. So Dave did actually have one other awesome idea, which is like, oh, you could just use diff. Like 1973 still works, but the sequences are like psycho long. So even if you had a diff, you're like going to be like paging through a multi-gigabyte file, so you cannot read that effectively. And like computer heuristics for like, oh, this looks weird, are beyond my ability. Like there are some guys that are doing like cool stuff with graphs and like taking differences for bug localization, and I'm sure it I'm sure it has potential, but I can't make it work because I'm not smart enough. So I just thought, okay, well, so here's the thing about code, right? It's like very, very structured. There are long sequences which are going to be repeated all the time because like, you know, like go to this object is going to be represented as like one string of assembly. So I can compress that with hierarchical grammars. So I stole like an algorithm from some academics that did all the hard work. So say you take a nursery rhyme which has got a lot of structure, and then you apply this algorithm, the Secateur algorithm, and you compress it from that to, what's that, 13 bytes, which is cool. And the reason it's hierarchical is because if you look inside the rules refer to other rules, which gives you huge, huge, huge compression. So now if you had to diff that nursery rhyme with like a 1-character change, most of these bytes would be identical, and then the changed characters like stand out like a sore thumb. So I saw that initially and I got like super excited. Then came the long cold winter of like it doesn't work. The grammar for the algorithm is generated on the fly because the way the academic guys wrote it is awesome. It's linear time. So whatever length the sequence is, the time is linear, which is fantastic for very long sequences. But because it's generated on the fly, if you run it over 2 different run traces, the grammars are different, which means you can't compare them, obviously, because it's like apples and oranges. So I had to write a recompressor. Like I had to compress the first one, then keep that grammar and write a tool to compress the second file with the same grammar, which is less efficient, but they can now be directly compared. So like the nitty gritty is probably boring. So anyway, I wrote a recompressor that converts it to a tree, which is a computer science thing. I'll use science. Then I apply the same grammar to the second file. So now I take all transitions from address A to address B, and I index those. Each transition gets an index in a database. So then that index of tuples, the tuple sequence, gets compressed. The variant also gets compressed. And then I diff them, like just with sdiff, and it's like unbelievably fast. And then I go back to the database from where I took the trace and I mark it up with some interesting info. So those of you that have seen my presentations before may be familiar with my annoying, hard to read green screen demos. And so now we have another one. How's that for size? We can go bigger? We can go bigger. Okay. Everyone read that fine? No. Okay, good. So what we're looking at here are the diffs converted into chunks. So the first chunk is like chunk 0. These are unchanged because, you know, it's like the loader. Starts at 0, goes through to call or ret number 1743, and compressed, it's 131 symbols long. The first time we hit a diff is here at like chunk 1. So rule number 20, or which could refer to the longest set is, I think, like 90,000 calls and rets, like 90,000 transitions compressed to a single rule. In this case, like rule 20 contains 80 fully, like when fully expanded, contains 80 transitions, and it's slightly different because, you know, there's like it's a bit longer. So if you feel like expanding all of those out and diving in, you'll like very rapidly go mad. It turns out that runs diff a lot more than you might think, like really a lot. Like if you run the same file, it'll also diff quite a lot. So you've got to be a bit selective about the stuff you're looking for. So I'm just going to press space now. This is the best demo ever. We need to shrink. Okay. So now these ones that aren't rules are transitions from A to B. They're not marked up as a module, which means they're either dynamic code, or this might actually be like in winword.exe. I don't know if for some reason it's not in the module list. The 1 is really interesting. The 1 means that this is the first time that transition has been hit. So this is where this is different from a graph. I have full sequence information available. So not only do I know the edges that were traversed, I know what order they were traversed in. And we'll come to why that's cool perhaps later in our mystical journey through green screen. Something interesting. Okay. Now the big arrow, like there's a small arrow and a big arrow. The big arrow means that this edge did not appear in the original file. So automatically that's now more interesting to me than the plain transitions, because this is like a transition that wasn't taken when it ran the non-faulting file, but was taken when it ran the faulting file. But it turns out that a lot of these dynamic addresses just change, like all the time. So once you like leaf through a few of them, you find that they're not fun. And I still need to make that smaller. Okay. So again, like annoying. We're getting closer, right? We're moving from an address in MSO, so we're in module space, but we're going to another one of these dynamic duvers. So we can see that like it's the same address, but it's just gone to a different whatever that is, say it's a dynamic address, and then come back also to the same spot. So not fun. This is why it's like, in my opinion, would be really complicated to try and do this automatically, because I can look at it, right, and say, oh, that's nothing. But how do I like write an algorithm that says, oh, that's nothing? Whereas you can see that code is basically identical, even though it's popping the diff. This is also where it's like a lot more complicated to do it with WinWord, which is massive, than like to do it for a POC. So, to cut a long story short, if I can remember how to use less, tick A, okay. So at chunk 285, so we're now 11 million calls in. On the right hand side we can see the first time we've gone from a real address, like an address in module space, to another address in module space. And that did not happen in the original file. So this might even be the bug. It's probably not. But it's like a good place to start. You can like start to see, oh, maybe I should like have a look at this particular offset. And this is now where